Okay, we have one more left, so let's take a look at yet another one. Very similar to what we've seen. We have a mechanism, 3 steps, and the first step asks us to find the overall reaction. And so we have to eliminate anything that's the same on both sides. So that N2O2, noticed, is formed and then it is consumed. I also have an N2O here that is formed and then consumed. So both of those are intermediates, and you can anticipate the next question that they're going to ask, which is, what are the intermediates? So we get 2NO plus 2H2. All you have to do is bring down whatever's remaining on the left-hand side of the arrow, yields N2 plus 2H2O. Now, our 2 intermediates were N2O2 and the N2O, and there's 2 reasons we would include those. One is that they are formed and then they are consumed. That's different than a catalyst, which is present and then reformed. These are formed and then consumed, and then they are not present in the overall balanced equation. So that would be your justification for those. All right, let's go on and see what else they're going to ask us about this. Now, from the mechanism, a student notes that they have this rate law, which is second order with respect to NO and first order with respect to N2. So that was pretty reasonable. You could deduce that and prove that if you needed to. But then the student says one that he or she thinks it's third order. And because of that, it's involving the simultaneous collision of 2 NO molecules and an H2 molecule. So it asks us, are these 2 conclusions correct? We do not have to prove that that is indeed the rate law. We don't have to. But in here, we look, the student concludes that it is third order, and that is true because for the first one first order plus second order is equal to a third order overall. So that's true. You want to note that. And then 2, you want to note is false or an incorrect statement. And there are a couple of ways that you can do that. The one way is that having a term molecular is not likely, but that's not enough. I think it's a good statement because it's unlikely that you can get 3 molecules to collide simultaneously with the correct energy and the correct orientation. But more importantly than that, there is not a single step in here that involves more than 2 molecules in the mechanism. And so it is, all steps of your mechanism are bimolecular. So you want to note that, not termolecular. So they made the wrong conclusion because they hopped back bimolecular. So they were just looking at the orders and not paying close enough attention to the mechanism itself. All right, now here it says explain why an increase in temperature increases the rate constant K given our rate law. So remember, we have our rate law. Rate was equal to K times NO squared times the concentration of A. So it says explain why an increase. We know that an increase in temperature increases the rate, but this one says to explain why. Well, we see here that there's got to be an increase in the rate, and the concentrations aren't changing. So therefore, your temperature must involve an increase in K. So if that's increasing and these 2 are staying constant, then K must increase. So you could make a statement like that. Now, one of the things that we have done is in our class, we've done the Arrhenius equation, which is K is equal to A to the minus E sub A over RT. Okay, well, if you increase T, right, you're going to, if you want to follow the logic, if you're going to use this, you need to be able to follow the logic. If you increase T, you're going to make this a smaller negative. That's smaller, and since it's negative, that results in an increase in K. So that would be an alternative way you can explain that. But here, I mean, hopefully it's pretty clear from the rate law expression that your temperature effects have to come into play with your rate constant K. So this was actually a quick one, and that is the last one I have for you. So until I see you in class, this is signing off.